let's do another math problem in CSS. Nim game 1. So what's going on here? We have n heaps and 2 players moving alternately, so it's another game, as you can tell from the title. So on every turn, you get to pick one of the heaps, and you move as many sticks as you want. And if you move the last stick from the very last heap, then you win the game. So the question is, given an initial state, right, some number of sticks, some number of heaps, some number of sticks in each heap, who wins under optimal play? So, for example, if we have 2 heaps, one with 4 sticks and one with 1 stick, the first player wins. And how does the first player win? Well, you can remove 3 sticks from the first heap. Now there's still 2 heaps with 1 and 1, and then the second player has to take away, kill one of the heaps, right? Remove, it's only says 1, so you have to remove the last one from one of them, and then you get to remove the last one from the other one, and then you win. So how do we solve this in general? So let me make a few observations, and then I'll tell you the answer. So the first thing is that there's only 1 heap, then the first player always wins by just taking everything, right? That's easy enough. And if there's 2 heaps, so if they're the same size, then you lose, actually. And the reason is, whatever you do to the first heap, the other player can do to the second heap, and then they're still going to be the same size. And eventually you're going to have to kill the first, remove everything from one of the heaps, and then the other player gets to remove everything from the other heap. And then they win. But if they're not equal, then you win. The first player wins by just taking away from the bigger heap to make them equal. Right? Recall from the last video that, the way a winning position is one from which you can move to a losing position, at least for these so-called impartial games where everyone has the same set of moves. Right? Anything the first player can do, the second player could also do. So you win if only if you can move to a position, to a losing position, right? And you lose if there's no moves to a losing position. Okay, so how do we actually solve it in general? We solved it for 1 heap and 2 heaps. So in general, there's actually a really interesting result, which is that it's a losing position if and only if the XOR of all of the different heap sizes, the sizes, is 0. Okay, so first of all, what do we mean by XOR? Let's just define that. So we'll give the examples for 4 and 1 and for 3, 5, and 6. So to do XOR, you write down all the values in binary, right? So 4 is 1, 0, 0 in binary, 1 is just 1 in binary. And then the result has a 1 if there's an odd number of 1s in that position, right? So for example here, there's 1, 1 in the 1's place, so that's a 1. There's no 1s in the 2's place, so that's a 0. There's 1, 1 in the 4's place, so that's a 4. And the XOR of 4 and 1 is 5. Let's do another one, the XOR of 3, 5, and 6. So right there in binary. So 3 is 1, 1 in binary, 5 is 1, 0, 1 in binary, 6 is 1, 1, 0 in binary. And the XOR, well, there's 2 1s in the 1's place, so that's 0. There's 2 1s in the 2's place, so that's 0. And there's 2 1s in the 4's place, so that's 0. So the overall XOR is 0. Right, so that's how you do XOR. You write it in binary, and then you compute every sort of place independently, just whether it has an odd or an even number of 1s. Okay? And so we're going to need 2 facts about XOR. So the first one is that the XOR of 2 numbers is 0 only if they're equal, right? Because if they are equal, obviously they either have both 1s or both 0s in the position, so you're going to get all 0s. And if they're not equal, then there must be some position at which they're different, and that one is going to have only 1 1, right? It's going to be a 1 bit in one of the numbers and a 0 bit in the other one, because they're different, so they must be different in some bit. Okay, so that's that one. The other thing that we're going to need to know is if we take an XOR and one of the bits is a 1, then one of the numbers that we XOR together must be at least that big. And in fact, it must also have a 1 in that position. And the reason is just that you get a 1 if there's an odd number of 1s, and if there's an odd number, it must be at least 1, right? So therefore, at least one of the numbers must be that big. So we'll need that later. Okay, so those are our 2 lemmas. So now we can actually see why this is true. Right, so the claim is that the position is lost if the XOR is 0. So we're going to prove that by induction, which just means that we're going to assume that it's true for the positions that we move to. Okay, so the easy case is if there's nothing, then that's a losing position, right? In fact, you already lost the previous turn because the last player won to move to that position. And the XOR of nothing is 0, right? That's the identity of XOR, so that's good. Okay, so what if we have a position and the XOR is 0? Then we want to prove that that position is a losing position. So if it's a losing position, that means that there's no moves to a losing position. Right? Any move that you make is going to leave your opponent in a winning position. That's just like the definition of a losing position. And so suppose we have any move from our position, and we take a pile that started out with A sticks, and then we leave it with B sticks. So the new XOR of all these piles, well, all of the old piles stayed the same. But there used to be an A in the XOR, and now there's a B. So this is the new XOR. Right, because we took out an A, which is actually the same thing as adding an A, because the XOR of anything with itself is 0, and then we added a B. And so for that move to take us to a losing position, we would have to have that A XOR B is 0. But that only happens if A is equal to B, and that's impossible, right? When you move, you have to take away some sticks, and then you have to have less sticks, so B has to be less than A. So if the XOR is 0, then you can't move to a new position when the XOR is 0. Right? Every move takes you to a winning position for your opponent. Okay? And so the other side is if the current XOR is not 0, then the position is winning. So it's winning if there's a move to a losing position. That is, if there's a move to a position where the XOR is 0. So we need to find that move. So how can we do that? So suppose we have the current XOR, write it in binary, and take the highest bit. Right? So in this example, that would be 4. Right? This bit. And it's non-zero, so that actually, there's at least one 1 in the binary representation. We're going to take the biggest one, right, the leftmost one. We must have a pile at least that big, right? That's this lemma. So we're going to move in that pile. And what we're going to do is take away, let's see, and this many sticks, b minus x minus b. Right, so the idea is we have the XOR. Let's say it's like this. We want to take away 4 sticks to get rid of this one, but then that would leave us with this one. So we actually only want to take away 3 sticks. Right. So the funny thing about XOR is that adding and subtracting is kind of the same thing. Right. So I guess you could try to make this 0 by taking away 5 sticks, but none of the piles are big enough to take away 5 sticks. But taking away 3 sticks has the same effect on the XOR of taking away 5 sticks. Right. So instead of b plus x minus b, which would just be x, right, which would zero it out, we can do b minus x minus b, and that also zeroes it out. So we'll see why that is. I'll go over that in more detail in a second, but that's sort of the idea. So there's 3 things we need to prove about this move. One is that there are actually enough sticks, that we can make this move. Right, that is, the current size of the pile has to be bigger than the number of sticks that we're trying to take away. Right, that was the problem with trying to take away 5 sticks from one of these piles. Neither of them is big enough. And so the reason for that is that this thing. So this thing is at least 0, right? Because b is just one of the bits of x. So b is less than x, less than or equal to x. And so this thing is at least b, because we're taking away some non-negative thing from it. So this thing is at most b, and p is at least b, right? So there's enough sticks in the pile to take away this many sticks. We should also prove that we're actually taking away, at least 1 stick, right? We can't take away negative sticks or leave the pile alone. So this has to be positive, strictly positive. And why is this? Well, x minus b is just x without its leading power. So it's the sum of some other powers of 2, right, in the binary representation of x. And the way that powers of 2 work is if you add together any number of smaller powers of 2, that still doesn't equal a bigger power of 2. Right? B is bigger than all of the other powers of 2 in x combined. And so that proves this number is positive. Okay, and so the last thing is that we should actually prove that the resulting XOR is 0. So we used to have p6 in the file, and we took away this many, so now there's this many. And so the new XOR is the old XOR, XOR p, because we took that, we used to have a p, and now we're taking it away, XOR the new number of sticks, which is p minus 2b, this is actually plus x. Not that it matters, because XOR plus and minus are kind of the same thing. So this is the XOR of, well, we have two p's, we have two x's, and we have two b's. And so they all cancel out with each other, right? The XOR of p and p is 0, the XOR of x and x is 0, and the XOR of 2b should also be 0. Let's see. Why should that be true? So what's going on here? So we flipped B, and we also flipped all of the lower bits. Right, we're subtracting off like this bit, and then we're adding on all of the other ones. And that is going to zero everything out. I think my arithmetic here is not quite right. But the argument is still right. Right? You're taking away this, and then you're adding back any lower powers of 2. And that flips all of them, which zeroes out the XOR. And because this one is bigger than all of these combined, you're still on net taking things away. Okay, so that's actually all that we needed to prove, right? We took an arbitrary position, and we proved that if the XOR is 0, it's a losing position, and if the XOR is non-zero, then it's a winning position. So now let's actually code that up. So we have a bunch of different cases, and each test case just has n and the numbers. So the coding, as usual in these math problems, is going to be much easier than this proof. Right, because we just need this. We don't need to know why it's true. Yeah, it's here or something. Speed in the numbers. XOR them together. Okay, this is the XOR operator. And if the XOR is 0, it's a losing position, so the second player wins, and otherwise it's a winning position, so the first player wins. And these. First, second. All right. Cool. So it worked. So yeah, as usual with math, the code is much shorter than sort of the explanation and the proof. So this is actually something worth remembering. Because as we'll see in later videos, this lets us solve basically any impartial games. Any impartial game, you can sort of think of as a game of nim in a way that we'll see later. And so knowing this solution to nim actually lets us solve like all of these games like this. So it is worth knowing that losing only if the XOR is 0. And this is why XOR is special. Yeah. So that's the poem.